Hello. This time I'm going to explain homework problem from section 8.1 of Pearson Calculus. Section 8.1 is about integrations. Okay, so first problem is just a review problem. Solve the quadratic equation by complete the square. In this section, we have to use the completing square technique in some programs. So this is going to be a review for that. So first of all, let's expand the left-hand side of the expression. So it's going to be x squared plus 2x minus 35 is equal to 13. Completing the square will allow us to make two different terms with x's into just a single x. It's going to become x plus 1 square minus 1. 半分にして、その2乗を引くという流れですね。Okay. Minus 35 is equal to 13. So bring all the constant terms to the other side of the equation. It's going to be 49. Since x is only in one point here, we just eliminate square and move 1, we can find x. So inverse of square is a square root, so it's going to be plus minus square root of 49, which is plus minus 7. So x must be equal to negative 1 plus minus 7. So x is either negative 8 or positive 6. Okay. Next problem is proving the identity. Okay, so this is just a review problem again. So it's a proof of the identity. So let's start from left-hand side. So left-hand side is tangent x to the power of 4 minus 1 over tangent x squared minus 1. Let's factor the numerator. So numerator, using the difference of the squares, it's going to be tangent square x plus 1 times tangent x squared minus 1 divided by tangent x squared minus 1. Now we can reduce these fractions. That is simplifies to tangent x squared plus 1. Here, we have to review something like it. And sine x squared plus cosine x squared is equal to 1 for all real number x. Divide both sides of the equation by cosine x squared. So divide both by cosine x squared. You're going to get tangent x squared plus 1 is equal to secant x squared. We will use this formula quite often when we are working with integrations. So by Pythagorean theorem, this is equal to secant square x, okay, which is equal to right-hand side, and that's complete the proof. Okay, next one. Now, I made a mistake for this one because I did a terrible subtraction errors. So is tangent of the arc cosine of square root of 11 over 5. The arc cosine of something will give us some kind of angle. So let theta is equal to the inverse cosine of whatever this number is. This means cosine of that angle is equal to square root of 11 over 5. And at the same time, there's a restriction on the domain. Theta is between 0 through pi. Okay. There are many angles satisfying this equation. But the arc cosine only will limit the answer in this domain. Okay. Well, because cosine is positive, it must be in the first quadrant rather than second quadrant. Okay. And the denominator indicates the hypotenuse, and the numerator is x coordinate. So using a Pythagorean theorem on this right triangle, you get y value is equal to square root of 14. Okay. So this expression is equal to tangent of theta, and tangent of theta, looking at this table, I mean this picture, it's going to be square root of 14 over square root of 11. Well, when you rationalize the denominator, it's going to be square root of 154 over 11. None. Okay. Next one is a review from chapter 3, which is derivatives. Number 4. Find the derivative of y with respect to v, which is y is equal to v times square root of 1 minus v squared minus inverse sine, arc sine of v. Okay, be careful here, the product here. Okay, so you have to use the product rule to differentiate. Also, this is a problem that is useful in this section because we have to know what is the derivative of this one. Okay, what is the derivative of this one? Okay, so y dash is equal to use a product rule, 左微分右プラス左 times 右微分。So derivative of u will be 2 square root of u, and the numerator is going to be derivative of the inside, which is negative 2v. Okay, derivative of this one is equal to 1 over square root of 1 minus v squared. So that's a formula from chapter 3. Okay, this is a formula. Now, let's simplify the middle term a little bit. So it's going to be 1 minus v squared square root minus v squared over square root of 1 minus v squared minus 1 over square root of 1 minus v squared. Well, let's combine these terms by make the denominators same, which means I multiply this one top and bottom by square root of 1 minus v squared. So the numerator becomes this. Second term is negative v squared on the numerator, and the third term is negative 1 on the numerator. So now combine the like terms on the numerator. It's going to be negative t 2v squared over square root of 1 minus v squared. Okay. Number 5. Now this is a program from this chapter, chapter 8. Okay, integral of a rational expression 8x over 4x squared plus 3 dx. This is a nice expression. It's a fraction, but you see that the derivative of the denominator is numerator. So we look at such expression optimistically to see, we hope that the expression looks like this form. Well, if this is it, then its integral is log of the denominator. So it's going to be log of absolute value of 4x squared plus 3. And you're going to just plug in 6 and 10. Well, you really do not need absolute value sign now because this function is always positive. So we can replace the absolute value sign with just a parenthesis for this case. Anyway, it's going to be ln of, it's 403 when you plug in 10, minus ln of 147 when you plug in 6. So that's going to be the final answer. But you can, of course, simplify the expression into single log by using the property of log. Can it be simplified? Can it be simplified? Well, denominator is a 7 times 7 times 3. So this fraction can be simplified only if the numerator is a multiple of 7 or multiple of 3. But 403 cannot be divided by 3, and it is not divisible by 7 as well. So this is in the simplest form. Okay, next one, number 6. The integral of x squared over x squared plus 8 dx. Well, we hope, like in the previous problem, the denominator's derivative is numerator, but it's really not. When you see a rational expression which has the degree, look at the degree. Degree of the numerator is greater than or equal to the denominator's degree is called improper. まあ、要するに過分数的なやつですね。In such case, it's not easy to integrate. So when you see something like this, improper fraction, first of all, divide it. Divide it to make it a mixed number. Okay, so I'm going to do the long division. So it's going to be like this. So the quotient is 1, and the numerator is -8. So after the division, it becomes like this. After the division, the rational expression becomes a polynomial plus some fraction, a proper fraction. So the numerator's degree is always less than the denominator's degree. The integral of y is very simple, and that's equal to x. But the integral of this one is a bit harder one. So the derivative of the denominator is not really the numerator. When you see something like this, the one formula you have to know is 1 over x squared plus 1. The integral of this one will be arctangent of x. Okay, so this is one of the formula that we have to master in this section. And this is very similar. The only difference is it is 8 here instead of 1 here. So how we do with this one? First of all, divide everything by 8. Divide top and bottom by 8. So it's going to be like this. And you want to rewrite this one like this. So 8 is same thing as square over square root of x, square root of 8. So it's going to be 8 over square root of 8 square plus 1. Okay, that's going to be our substitution. Now it's going to be substituted like this. So u is equal to 1 over square root of 8 times x. Then du will be 1 over square root of 8 dx. You are not going to substitute this part. This part is done. We're just looking at this part, okay? So after the substitution, it is going to become u squared plus 1 times square root of 8 du. Square root of 8 is just a constant multiple, so you can put outside of the integrand. So it's going to be integral of u squared plus 1 over that du, and now you can use this formula. So it's going to be x minus square root of 8 arctangent of u, and u is equal to x over square root of 8. Okay, so that's going to be the answer. Of course, you can simplify the square root of 8 as a 2 square root of 2. So if you do that, it's going to be looks like this. If you do not like the radical in the denominator, you can, of course, change it to x square root of 2 over 4 if you want. Okay, next one. Number 7. Integral of 6 minus 72x over square root of 1 minus 32, 6x squared dx. Well, do you see that the derivative of the inside here is equal to here? So that's nice, but you have some extras here. When you have addition or subtraction on the numerator, you can always split into 2 fractions. And we can do the integration piecewise. So let's break this one into this piece and this piece. The second one seems to be simple because if you say u is equal to this, then that derivative is basically here. So that's basically done. So let's do this part first. Okay. This side is actually, you have to use a different substitution, and you really need to know one formula for this shape. And I'm going to explain that one later. So first of all, this one is u is equal to 1 minus 36x squared. Then du is equal to negative 72x dx. So after substitute this one, including this negative here, it's going to be du over square root of u. And that is equal to 2 square root of u plus c later. So it's going to be 2 square root of 1 minus 36x squared. This one, the key formula you want to know is this. So sorry. The key formula you want to know is, remember the derivative of the inverse sine function was 1 over square root of 1 minus x squared. So the integral of 1 over square root of 1 minus x squared dx is equal to inverse sine function. So this part, if we say this part is equal to u squared, then we can make it look like this. Okay. So for this part, let's say u is equal to 6x. So du will be 6 dx. After this in substitution, it's going to be square root of 1 minus u squared on the bottom, and numerator will be 1 du. So using this formula, the integral of this one becomes the inverse sine of u, which is equal to inverse sine of 6x. Okay. So you have to know this one. And you have to know this one. The antiderivative of arctangent and antiderivative, antiderivative that gives the arctangent and the arcsine. Okay, number 8. 9 through 10 of 5, 82 plus x squared minus 18x dx. This is a proper fraction, so you don't need to do division. Derivative of the denominator is not equal to the numerator at all, so you cannot use log. When you have a quadratic expression like this, there are 2 types of the problems. First type is something you can factor into two linear terms when the when the quadratic function has two real solutions, you can split into two different simpler fractions. That's something we're going to cover in later sections. Another thing is when the quadratic function has no real roots. In such case, you have to use completing square to make the denominator looks like this. Okay, make a denominator complete a square to make square plus square. So that's going to become closer to the derivative of the arctangent. So you do the complete square, it's going to be half. So it's going to be x minus 9 square minus 81 plus 82. So that's going to become 5 over x minus 9 square plus 1 dx. Do you see this? This looks like identical to this. The only difference is it's a linear change in here. So basically, this expression is the same thing as this one. Let's use the substitution to make it clear. So let's say u is equal to x minus 9. Then du will be dx. And when x is 9 and 10, u is become 0 and 1. So it's going to be 0 through 1, 5 u square plus 1 du. 5 is just a constant, so you can just leave it as 5 times arctangent of u, and 0 through 1. So it's going to be arctangent of 1 minus arctangent of 0. So for what angle the tangent becomes phi and 1 between negative 90 degree to positive 90 degree. So tangent becomes positive 1 at pi over 4. Okay. And the tangent becomes 0 when angle is 0. Okay. So the answer is 5 pi over 4. Okay, next one is looks ugly, but it's kind of similar to this problem. So number 9 is integral of negative this divided by 4 to negative square root of 3 minus 1 over 4. 24 is just a numerical constant, and 1 plus linear term squared. So again, this is already in complete squared form. So it's a square plus square. So it looks like 1 plus u squared and 1. So its problem is basically identical to this. So you will make a substitution. So let's say u is equal to 4x plus 1. So du will be 4 times dx. The ugly number for x. Ugly number for x, but after you do the substitution, it's gonna be square root of 3 here and negative square root of 3 here. So negative square root of 3, positive square root of 3. Bottom gonna become 1 plus u squared. Okay, so that's like this form, and the numerator will be 4dx, 4dx, 4dx will be du, so it's gonna be 6 du. Okay, so 6 is just a constant. We can use this is a negative a to a, so maybe you can use the even functionness to make it to 2 times that, because this is even function. The integral of this will be arctangent of u. And you substitute square root of 3 and 0. So for what angle between negative 90 degree and positive 90 degree to give you square root of 3? So tangent becomes square root of 3 when the angle is 60 degrees, so it's going to be pi over speed. Then The tangent becomes 0 when the angle is 0. So the answer will be 4 pi. Number 10. Number 10 is a complicated one. Okay, looks very complicated. You might wonder where to start with. You notice that y on the bottom can be factored out. So this expression is equal to expression in terms of ln y and the derivative of ln y here. So let's say u is equal to, so let's say u is equal to ln y, because you have ln y's derivative here. Okay. So du will be 1 over y dy. So after making a substitution, it's going to be u cubed over 2 plus 9u to the power 4th du. Now the things look straight. You see that the derivative of the bottom is top, which is nice. So basically done. Derivative of this is equal to 36u cubed. So 36, we don't have a 36 here, but we can multiply top and bottom by 36. So now numerator is the derivative of the denominator. So it's going to be 1 over 36 log of 2 plus 9u to the power 4th plus c. Bring back u in terms of x. It's going to be 2 plus 9 ln y to the power 4th. This 4th is outside of ln, so we will need a parenthesis here. Plus c. Okay. This one you don't need absolute value here. Because, well, you start with absolute value, but you can remove it because this is always positive for any value of u. Okay, so that's going to be the answer. Okay, number 11. So that's rational expression. We hope the derivative of the denominator is numerator, but clearly not. And it's impossible because it's an improper fraction. It's improper. The degree on the numerator is greater than degree in the denominator. So first things you should do is do the division to make it to sum of polynomials and the proper. 割り算で、直しましょう。So it's going to be 10t squared cube minus 3t squared plus 10t plus 0 and t squared 0t 1. So you do the division. So it's going to be 10 and it's going to be negative 3. And so that's going to be the remainder. So it's going to be 10t plus minus 3 plus remainder over t squared plus 1. Okay. Now you see that this one, the derivative of the denominator is not equal to numerator, but you see this is antiderivative. This is arctangent case. So just integrate piecewise. It's going to be 5t squared minus 3t plus 3 times the arctangent of t plus c. Okay, so improper, divide and integrate each piece. Okay, next one. Number 12. So 9 times square root of 1 plus cosine theta d theta. Well, this is a hard one because you see that the derivative of the cosine is nowhere in this program. So it's kind of not easy to see how should I make a substitution. Okay, let's multiply top and bottom by its conjugate here. Okay, so this is one technique. When you see 1 plus cosine or 1 minus sine, something like that, the 9 is out. You 9, so 9 is just a constant multiple, so you can put out. So multiply 1 plus cosine by its conjugate on top and bottom, which is 1 minus cosine and 1 minus cosine. Okay. Then what we are going to get is the numerator going to be square root of 1 minus cosine square. And 1 minus cosine square is same thing as sine square. Sine square. So you can remove the, you can get the sine out of the square root sign. Be careful though when you remove the square root sign, that in general, the square root of a square is not equal to a. That's not true. The correct rule is absolute value of a. Okay. And if a is positive, we can remove absolute value sign, but you have to check whether this is positive or not. Okay. Fortunately, first of all, remove the square root sign. You want to get absolute value of sine theta. Fortunately, because theta is between 0 through pi over 2, as indicated here, sine theta is positive in that range. That's why you can remove absolute value sign. Okay. This expression looks worse than the original expression because it's a fraction. Now you have more complicated stuff. But the good thing is when you make a substitution, you see its derivative is here. So now you want to say u is equal to 1 minus cosine theta. Then du will be sine theta d theta. Now the theta is between 0 through pi over 2. When theta is equal to pi over 2, cosine pi over 2 is equal to 0. So u is 1 minus 0, which is 1. When theta is 0, cosine 0 is equal to 1. So u is 1 minus 1, that is 0. So after the substitution, it's going to be 0 through 1, square root of u on the denominator. And the numerator is combined together to become just du. So using a power rule, this is going to be square root of u times 18. And just plug in 0 through 1. So it's going to be 18. Okay, next one is number 13, another integration, which looks complicated. 7dx over x square root of 16 minus 49 ln x squared. Looks very complicated, but the things to notice is what if inside the square root is u? Then that derivative is unfortunately not so good. The derivative of ln x is equal to 1 over x, which is here, which is nice. But the derivative of ln x squared is not so nice. Yeah, because it's going to be 2 ln x over x. That's bad. So instead of making a substitution for everything inside the square root, let's notice, pay attention to this part is as a square of something. So let's say u is equal to 7 ln x. Okay, 7 ln x. Okay, and let's see what's going to happen. Then du will be 7 over x dx, which is everything outside of the radicals. So that's a good start. So that's going to become du on the outside, and the inside is going to be 16 minus u squared. Now this looks good because it looks like this format. So it's similar to arc sine x. Well, instead of 1 here, you have 16 here. So you have to use a formula for a squared minus x squared instead, which I really don't remember. So if you remember the formula for this more general version of the arc sine, then use that one to get the answer immediately. If not, you have to make a better substitution, or you will make another substitution. So let's put 16 outside of the right integral. So let's put 16 outside like this. So factor out 16, you want to get this. Okay, so that's going to become 1/4 integral of du over square root of 1 minus u over 4 squared. Okay, so this is basically you can take arc sine because difference is just like 1/4. It's a linear change. So it's kind of integral of ax plus b of f. That's going to become f, ax plus b, but be careful, just divided by a later. So at this point, I can use arc sine. So it's going to be arc sine of u over 4. Oops. Not arc sine of u over 4, but I had to divide it by 1 over 4. Okay, so I had to divide it by 1 over 4, so which means multiply by 4. So after simplify it and bring back to x, it's going to be arc sine of 7 ln x over 4. Okay. So if you feel this is like too much, then maybe use this formula for this version. If not, then like I do, just memorize this basic shape form and get used to with a linear change. Linear change doesn't affect how the answer looks like, except the factor of 1 over a at the end. Okay, now this one we really need a calculator. Okay, 7 through 12 of 2x to the power 5 over x cubed minus 3 dx. First things to notice for this rational expression is this is improper because degree on the numerator is greater than degree in the denominator. So let's do the division. Okay, so it's going to be 2x squared, 2x to the 5th minus 6x squared. So that's going to be 6x squared. Now the degree of the divisor is greater than degree of the remainder. So division is done at this point. So it's going to become 2x squared plus remainder over divisor. Now we hope this fraction, the denominator's derivative is numerator, and it is, because derivative of the denominator is 3x squared. So it's just like a constant multiple difference. So we can use this idea. So it's going to be log of f, log of f. Okay. Integral of this one is just the power rule, 2/3 of x cubed plus 2 times ln of x cubed minus 3. Okay, now you plug in numbers. It's going to be 12 cubed plus 2 ln 12 cubed minus 3 minus 7 cubed minus 2 ln 7 cubed minus 3. So let's combine this part as 2/3 times this. And the second part is ln of 12 cubed minus 3 over 7 cubed minus 3. And remember, ln of a minus ln of b is equal to ln of a over b. I hope we can simplify this part. 12 cubed is 1728, 7 cubed is 343. And you do the same thing here, it's going to be 1725 over 340, which looks nice. It's going to be 1485. No, 1485, no, 1385 plus 2 ln. Top and bottom is multiple of 5, so divided by 5, it's going to be 345. Okay, and the bottom is 2 times 2 times 17, and numerator is not the multiple of 2 and 17, so this is the simplest we can get. This is not the multiple of 3, so we cannot make it much simpler. So it's going to be 2770 over 3 plus 2 times ln of 345 over 68. Okay, so that's the exact solution. And because it's set around to the nearest thousands. Well, maybe I'm missing a digit here, but I'll do the calculator. So I have to use the calculator to check the answer. So I don't know why I got the correct answer here, but according to the calculator, it's 296.58140. So I'm kind of off here, but yeah, I guess the correct answer is 926.581 because this is to the nearest thousands. Well, when I was solving this one, I thought it's to the nearest hundredths. So I only did it up to this one, but anyway, let's move on to the next question. Okay, number 15. Okay, number 15. Well, I hate theta, so I just write down everything in x. Like last time, this is an improper fraction. So let's do the division. Q square linear constant, 3 minus 5, so divide it. You can divide more. And you can divide more. So the quotient is 2x squared minus 4x plus 3. Remainder is 15. You see this one, the derivative of the denominator is numerator. It's just a constant multiple difference. So you can use the log. So after integrating each term, it's going to be 2/3 x cubed minus 2x squared plus 3x plus, well, this is 3 times 5. So it's going to be 5 times ln of absolute value 3x minus 5. And don't forget to add constant c. Okay. If you rewrite everything in terms of theta except instead of x, you are done. Okay, last question. Number 16 will be a review from a volume question in chapter 6. So you have a y is equal to 9 cosine x, 9 cosine x. Y is equal to 9 cosine x. So the y-intercept is 9. And y is equal to 3 secant x. So y-intercept is 3 and the secant x is 4 like this. Okay. We don't know when they are going to meet, but the question says integrate between negative pi over 4 through positive pi over 4. At pi over 4, the cosine, 9 times cosine of pi over 4 is 9 over square root of 2, which is same thing as 9 over 2 square root of 2. For the second one, this one, y is equal to 3 secant x. So that's going to become, at 45 degrees, it's going to be 3 times square root of 2. So at this point, the secant graph is still below the cosine graph. So at the problem state, the cosine is always above and the secant is always below in this interval. Okay. The problem is we're going to generate the volume, the solid, by rotation with respect to x-axis. So I have to use the washer method. So volume will be pi times the bigger radius square minus pi times the little radius square over the interval of negative pi over 4 through pi over 4. Well, clearly everything is even. Really, this side and this side is identical, so you can use evenness to make it to double the result of 0 through pi over 4. I'm using even property. The bigger radius is the y value for the upper graph, so which is 9 cosine x. Okay. The bigger radius is this length. That's the length, so that's going to be y value for this curve. And the little radius is the y value for this function, so that's going to be 3 secant x. So this problem is basically asking for integral of cosine square and the secant square. The antiderivative of secant square is tangent x. So this one is done. The integral of cosine square, you will need a technique, which is called half angle identity. So when you have to integrate the cosine square or sine square, you have to use the half angle identities, which lowers the degree of the powers on the trig function. So when you see a cosine square of x, change it to this. When you have to integrate sine square of x, change it to this. Both of them is a double angle of cosine. Okay, that's something we have to use to rewrite this expression to integrate. So it's going to be 2, 1 plus cosine 2x. Okay, then you can integrate everything. So let's simplify into 3 pieces. So first piece is 81 pi 1 dx. Second piece is 81 pi cosine 2x dx. And the third thing is 18 pi secant square x dx. Each term is integrable. Here is the same number here as this one. So integral of 1 is x, 0 through pi over 4. Integral of cosine 2x will be sine 2x, but you have to divide it by 2. 0.0354. And the integral of secant square is tangent x. And again, 0.0354. So this will become 81 pi times pi over 4 minus 0. When you plug in this one into pi over 4 here, sine pi over 2 is 1. And sine 0 is 0, so it's going to be 1 here. Tangent pi over 4 is equal to 1. Minus tangent of 0 is equal to 0, so that's just 1. So after simplify it, you want to get 81 pi square over 4 plus these are like terms, so it's going to be 45 pi over 2. Okay, so that's going to be it. So that's complete explanation for homework section 8.1. Next time I'm going to explain section 8.2, which is about the integration by part, which is a very important technique in integrations.